Filtered indexes offer three primary advantages. They improve query performance, in part by enhancing the quality of the execution plan. The maintenance costs for the index are smaller because the index needs updating only when the data it covers changes, not across every row in the table. And the index requires less storage space because it covers only a small set of rows. You should use filtered indexes with sparse columns in these kinds of scenarios, when most of the data in the field is null, such as with sparse columns. For columns that represent categories of data, such as a part category key. And then for columns with distinct ranges of values, such as ranges for months, quarters, or years. Database administrators can also create filtered statistics, which create input for the query optimizer based on subsets of data. So let's take a look at how you can use filtered indexes. Here's an example of creating a filtered index on a table. So I use the create index statement, like creating any index within SQL Server, give it a name, in this case calling it filtered index dog_cs_weight, on dog_cs. And that's a table created that has sparse columns as well as a column set column. And I want to create the index on weight. And then here's where this becomes a filtered index, because I have a where clause and I only want to create the index on rows in the table where the dog's weight is greater than 40 pounds. So this index is not going to include any rows that have a null value for weight. Okay, so I'll go ahead and create this index. And then I can execute this kind of a select statement. Okay, nothing fancy there, just retrieves the dogs with weight greater than 40. But where it becomes interesting is if you look at the execution plan. So here's the execution plan. Well, the bad news here is that SQL Server, specifically the query optimizer, decided that mainly because there are so few rows of data within the table, it was quicker and more efficient to use a clustered index scan. So it used the index that was created on the primary key in order to scan through all of the dogs in order to find the dogs with a weight greater than 40. Okay, so this shows how even though there's an existing filtered index on that table, the query optimizer, it's not guaranteed that it'll use that index. Okay, let's take a look at a little bit better example. So in this case, I have some code that's going to use some data in the AdventureWorks 2012 database. That has bigger tables, more data to work with. Okay, and specifically, I'm going to use data from the sales order header table. So I'll execute that. That's just a select star from the table. And you can look at the nature of the data. So it's sales order information, order date, due date, ship date, and so forth, online order flag, and so forth. But we have a column that is a good candidate for a sparse column, the currency rate ID. As I scroll down, you can see that there's a fair proportion of the rows in this table, in all 31,465 rows, that have null values. So this is a candidate to be a sparse column. Microsoft didn't make it a sparse column, but we can still use filtered indexes on that column. And then another candidate would be the comment column, but it turns out that there aren't a whole lot of comments. In fact, there are no comments. So that's not quite as interesting and useful. Okay, so what I'm going to do is I'm going to create this filtered index on the sales order header table where the currency rate ID is not null. So I'm calling it FISOH, currency not null. It's on the sales order header, and it's indexing the currency rate ID. And here's what makes it a filtered index. I'm setting a predicate so that it's only going to filter the rows where the currency rate ID is not null. All right, so I'll go ahead and create that index on the table. Okay? And then we can execute a query like this. So I'm looking for a currency rate ID of 6266. So these are all the sales orders that use that currency rate. Okay, I can look at the estimated query execution plan. And here you can see that this item right here uses that index, the FISOH currency not null. And I can hover over it, and I can't move the cursor, but you can see down at the end of the output list, it says sales order header currency rate ID. So it's outputting that clause. And then under the object, it's using both the table itself, well, of course, it has to get the data, but then also the FISOH currency not null index. That indicates that execution plan is using that index. There were enough rows in the table in order to make it worthwhile, more efficient, to use that index. Now, you're not limited to using filter indexes with just non-null data. You can also create an index on ranges of values. So here's a statement that creates a filtered index where the subtotal value is greater than 20,000. Okay, so I can create that filtered index. And then here's a couple of queries. So here's one that filters the data where the subtotal is greater than $30,000. Execute that. Returns 1,125 rows. We can look at the query execution plan and notice that it didn't use that index. So again, the query optimizer decided that the query wasn't going to execute more efficiently by using that index. But here's one where it does use the plan. So now we're looking for subtotals between 21,000 and 23,000. Once again, look at the estimated execution plan, and you can see that it uses that index, the FISOH subtotal over 20,000. The idea here is that because this query returned a much smaller set of rows, apparently it was more efficient when it uses that index.